Hello and welcome to the midterm take-up video. We're going to be looking at midterm number 2, the B version of the midterm, and I will be showing the solutions for this B version of the midterm. And before we get started, just a quick note, many of the questions have different bonus marks attached to them. So with each question, I'll be letting you know what the maximum number of marks you could have gotten on the question are. In question 1, which is where we're going to be starting, there are 8 marks allotted to the question, but in fact there are actually 12 true and false questions, and each question is worth 1 mark, so the total number of marks available in question 1 is 8. So going through question 1, the things you need to know are that there are 1 mark per question, and marks are given only for a reasonable justification. So getting a true or false correct will not give you a mark, getting a justification correct will. Part A. As the frequency of a sinusoidal voltage source increases, the impedance of any capacitors in the circuit also increases. If you look at the impedance of a capacitor is equal to minus J over the frequency times the capacitance. So therefore, as the frequency increases, the capacitance actually decreases. This is false. We'll write that so you can see it. There we go. Part B. As the frequency of a sinusoidal current source decreases, the impedance of any inductors in the circuit also decreases. So if you take a look at the inductors, Z of an inductor is equal to J theta L. As the frequency decreases, the impedance in fact does also decrease, so this is a true statement. Part C. As the frequency of a sinusoidal voltage source decreases, the impedance of any resistors in the circuit also decreases. The impedance of a resistor is just equal to R, the actual resistance of the resistor. Impedance is real for a resistor. And in this case, the impedance is not a function of theta, so this is theta independent. So this statement is false because the sinusoidal voltage source frequency changing does not change the impedance in any way, shape, or form. Part D. A first-order RL circuit is structurally the same as a parallel RL circuit. In this case, you need to make some assumptions as to what you mean by structurally the same. In my argument, I would say that structurally the same is equivalent to having the same differential equation. So structurally same is equivalent to same dynamics or the same diff EQ. In this case, we do know that they're the same, so this would be true. A circuit built with only capacitors and resistors must be a first-order circuit. This statement, in fact, is false. So we do know that if we have 2 capacitors that are in parallel or series, you can put them in terms of an equivalent capacitance. So this is equal to 1 capacitor, but that's not true if we have pieces that are more tied together. So if, for example, you consider a resistor and a capacitor together, and you have a second resistor and capacitor together, this does not have one single equivalent circuit, and in fact, this is not a first-order circuit. In this case, each branch induces its own differential equation, and this is not first order. Part F says that a second-order series RLC circuit is structurally different from a parallel RLC circuit. If you consider structural equivalence to be the same dynamics as we had above, then this statement is actually true. They are different. They are different because the structure induces a different differential equation. Moving on to the next page, number G. For every series RLC circuit, there is a sinusoidal frequency for which the current going through a voltage source is in phase with the voltage when in steady state. In order for the current and voltage to be in phase, you need to know that the equivalent impedance of the whole circuit is equal to a real number? Well, if you consider the capacitor and the inductor in series with a resistor, then the equivalent impedance is simply equal to R plus J theta L minus J over theta C. And in fact, if you combine the complex parts together, you have J times theta L minus 1 over theta C. It's very easy to find a solution where theta squared is equal to 1 over LC, in which case you can actually remove the complex part. So this statement is true. Number H, if all voltage and current sources are operating at the same frequency, then it is always possible to use the method of practical source transformations to find an equivalent Thevenin circuit. This is false when you look at a DC circuit and is therefore also false when you look at AC circuits. The reason that this is false is because this only works if you can do a practical source transformation. When can you do a practical source transformation? Well, you can only do a practical source transformation, let's finish writing that, if you have a voltage source in series with a resistor or a current source in parallel with a resistor. If, on the other hand, you have a voltage source that is not in series with a resistor or a current source that has a resistor in series with it, practical source transformations will not work. Number I, if a circuit has a sinusoidal voltage source with a DC offset, then the steady-state currents and voltages in the circuit can be solved with a KVL and KCL equation on a single impedance circuit. So if you look at this, you realize that you need one circuit for theta is equal to 10 rads per second. But you actually need another circuit to solve for the DC value as well. And DC, by the way, is equivalent to theta approaching 0, or theta equals 0. So in fact, you need two. And you cannot do this with simply one equivalent circuit. This statement is false. Part J. If a circuit has two parallel branches, where the first branch has a series resistor and capacitor, and the second branch has a resistor and inductor, then there is always a sinusoidal input frequency for which the two parallel branches have a purely real impedance. Now we do know that if RC is equal to RL, in other words, the resistors that are in series with the capacitor and with the inductor have the same resistance values, then this is true. And in fact, this is true at the resonant frequency, theta squared equals 1 over LC. But in general, if RC is not equal to RL, this cannot be guaranteed. And this statement is in fact false. Now, it takes a fair amount of work to show that. I'm not expecting you guys to do that fair amount of work to show it, but I am including an actual set of equations here to show you that. So let's take a look at this. If you consider the capacitor in series with a resistor and the inductor in series with a resistor, then the equivalent capacitance of this parallel branch is equal to the RC minus J over theta C value of the left side and the ZL equivalent impedance of the right branch, which is just RL plus J theta L. So if you look at the two branches in parallel, you have one times the other over one plus the other. And when you rearrange this in order to get what you're looking at, then you notice that you have a numerator and a denominator. In general, you can't make the actual complex terms disappear between the top and the bottom because the complex terms are not the same in the top and the bottom. So you notice that when you're looking at the top, you're going to get a term that looks like RC theta L minus RL over theta C. And if you look at the bottom, you have a term that simply has the theta L minus 1 over theta C, the regular resonant frequency. So you can't make those disappear by setting it equal to 0 because there's no way to set both the top and bottom equal to 0. The only way that you could make them actually cancel out is if on the top the ratio of complex to real is equal to the ratio of complex to real on the bottom. And that is set out in this equation over here. So if you can find an equality there, then what would happen is that you have the same complex angle on the top as you do on the bottom. When you do the division, the angles subtract out and get back equal to 0. So let's look at this equation and see if that's actually possible to do. Well, when you take that equation and you do a little bit of rearranging, then you can see that at the end of the day, that will only be possible if you set theta squared equal to some ratio of numbers, which you can follow the math on this page to figure out. The problem is that the numbers on the top and bottom in here are not necessarily positive. So you cannot generally assume that there will always be a solution. There will be times when there's a solution, and there will be times when there is no solution. And what that depends on is essentially whether you're able or not able to ensure that these numbers are both positive. If either one of those numbers are negative, then theta would be a complex number, but of course frequencies have to be real, so that would not be possible. So in this case, this is a detailed proof that the answer to that question is false. Part K. A circuit with a voltage source and a current source operating at two identical frequencies can be represented with one Norton equivalent circuit. This statement is true. We know that as long as there's one impedance circuit, every impedance circuit has either a Norton or Thevenin equivalent. So since there is only one frequency, there's one impedance circuit, and this is true. So we know. Lastly, when a capacitor and inductor are in series, their total impedance is always real whenever L equals 1 over C. This is blatantly false. We know that theta squared equals 1 over LC gives us a value of impedance which causes it to be real, but when we have L equals 1 over C, that only becomes real if it just so happens that the resonant frequency is equal to 1. That is not necessarily the case. That is governed by other factors.